Welcome everyone to lesson 1.10 of Precalculus. Today we're going to be talking about rational functions and wholes. So we're finally going to explore this weird phenomena of rational functions a little bit further. So let's get started. So let's explore that concept in question 1 here. So let's find the whole of the following rational function graphically. So graphically, a whole, you'll see it is an open dot on our graph. You can see that here. Our whole is at 1, 2, 3, x equals 3. So our limit notation, well, where are the y values getting closer and closer to? So my graph is not quite as accurate as I originally thought it was. For some reason, it is not getting close to the value I wanted it to, but it should be getting closer and closer to 1 from the left and 1 from the right. So you'll notice that for wholes, our limit notations are going towards the same places when we use this one-sided limit notation. So that's kind of interesting. So let's find a whole numerically. So numerically means that we're going to be plugging in values and seeing how that is. Before we do that, just for me, kicks and giggles, analytically, I want to factor this as much as I can. So I'm going to have 10 times x plus 3 in the numerator, and I'm going to have x plus 3 times x minus 2 in the denominator. So I know that 3 is a 0 for both, and 2 is a 0 for the denominator. So I know that there's a vertical asymptote at 2, but negative 3, my bad, is going to be where the whole is. So we're going to plug in some values to the left of negative 3 and to the right of negative 3 and see what happens. And I have gone ahead and done that for us. I got negative 1.961, negative 1.996, negative 1.999, and something really close to negative 2. Then on the other side, we get negative 2.041, negative 2.004, negative 2.001, and something approximately close to negative 2. So what is happening here? Well, this means that on the left-hand side, the limit as x approaches negative 3 from the left of g of x is negative 2. From the right is also negative 2. So since they're both going in the same place, so since the left and right are both going towards the same value, we can actually combine these two one-sided limits into a two-sided limit, a regular limit. So we can just say that the limit as x approaches negative 3 of g of x is equal to negative 2. We don't need to put both sides for wholes. So that makes our life a little bit easier. So we've done this graphically. We've done this numerically. Now we're going to kind of combine all of that. So I got a little warning for us. We need to pay attention to what sets this question apart from the other ones. So I see what sets this apart, and I can see that there's this nice quadratic here, and this quadratic is not factorable. That's awful. Since it is not factorable, what I'm going to do is I'm going to see if we have any zeros. Well, first of all, I know that 1 and 1 here means that 1 is going to be a whole, but I want to see what happens everywhere else. So this is a quadratic. It's really weird. I don't want to touch it right now. Let's make a chart. So if we're not sure, we can always make a chart of inputs and outputs. And because we got a whole at 1, let's make that the middle. So we get 1, let's do 0, negative 1, and negative 2, just to give us a clear picture. Now, when we find out what the shape is, you'll see why 1 was really, really nice. If you don't get numbers that make a really nice shape on your graph, pick more numbers. There's no rhyme or reason to you have to use these numbers. Always start with 1. No. Pick numbers that are going to show up nice in your graph, and you don't know what those are to start, so pick some and have fun with it. We already know that 1 is an error because it's whole. But if I plug in 0, I'm going to get 4. If I plug in -1, I'm going to get 1. -2, I'm going to get -4. And I'm going to see that I'm going to get a mirror result on the other side. Now, you can plug all those in. You can use a calculator. You can do it by hand. It really doesn't matter. I'm going to plot those points. I already know that's not going to show up nice in the color I like to use. So I know that 1 is an error, so I'm not going to touch 1 right now. But 0 is 4. -1 is 1. And -2 is -4. I know that 2 is 4. I know that 3 is 1. And 4 is -4. So that's all fine and dandy. What happens at 1? Where is the hole? How can I figure that out? Well, we already have this set up quite nicely where we have a linear factor and a linear factor and they can cancel. We do have to remember that it doesn't exist at 1, but they cancel. So the graph's behavior is going to be that of what's left. And what's left is this -x² plus 2x plus 4. And we can plug -1 into that and see what happens there. So -1 squared plus 2 times -1 plus 4. Negative squared is positive, so we have -1 minus 2 plus 4. And I made a mistake. We plugged in a -1 for some reason. It is a positive 1, Mr. Whaley. That gives us 5. So even though there's an error, it does not exist, there is a hole at 1, 5. So this is what our graph looks like. So it follows the behavior of this function. It follows the behavior of the part that didn't get canceled out. Except we have to remember that it doesn't exist at the values that we canceled out at. So it doesn't exist at 1, so that's why we put a hole there. But its behavior follows that along. So we end up with a nice quadratic with a hole at its vertex, which is really cool looking actually, which still makes it entirely symmetrical, which is quite nice. So we talked about multiplicity with vertical asymptotes last time. We said that if the multiplicity was higher in the denominator, then it doesn't matter if it exists in the numerator. If its multiplicity is higher than the denominator, it's a vertical asymptote. So it's a hole for a rational function if the degree in the numerator is higher or if they're the same. So we can compare these multiplicities, higher in the numerator or equal, whole, higher in the denominator, vertical asymptote. So a little bit weird, but not as much if you think about it. So instead of just taking everything at face value, play around with some of these things. Try to think about them logically and mathematically and see what makes sense to you. So our last one here is going to deal with that multiplicity. We have 2 with a multiplicity of 2 in the numerator. The denominator factors to be x plus 6, x minus 2, which gives us 2 and -6. So our domain doesn't include -6 or 2, so -infinity to -6, -6 to 2, and then 2 to infinity. Whole, since 2 has a higher multiplicity in the numerator, x equals 2 is our whole. Our 0, well, we have none, because it's a whole. Vertical asymptote, our unique 0 was -6, so x equals -6. Horizontal asymptote, well, they do have the same number of zeros, which means the degrees are the same. Degree 2 in the numerator, degree 2 in the denominator. If we look at the leading coefficients, we would still get y equals 1 over 1, which is just 1. And our end behavior, well, that requires us to write it as a limit. So the limit as f of x, as x approaches -infinity, would be 1. Limit as x approaches infinity of f of x is also 1. One thing that we didn't include here was a limit notation for the whole and a limit notation for the vertical asymptotes. I'm going to go over that, but unless it specifically asks you for limit notation or it says end behavior, you don't technically have to put the limit notation. But I'm doing it just to show. So for the whole, if I cancel out one of the common factors, I would have the function x minus 2 over x plus 6. So the whole, if I plug in negative 2, would be 0 over 8. So the limit as x approaches 2 of f of x would be 0 over 8, or just 0. Vertical asymptote, we can plug in a really large, or number really close to 6 on both sides, see what happens. I'm going to just go ahead and say that the limit as x approaches negative 6 from the left is infinity. Or I need to put the function name. F of x is infinity, and the right-hand side is negative infinity. And how I do that is I test a value, again, really close to that side, and see what happens there. I do it numerically most of the time. But again, unless it specifically asks you for the limit notation of the whole, limit notation of the vertical asymptotes, you don't have to put those. But end behavior, if it uses the words end behavior, it is expecting limit notation. That is it for this lesson. Hopefully that wasn't too bad. If you have any questions, please make sure that you ask. Otherwise, I'll see you in the next video.